All right, how's it going? So hopefully everybody turned in PA4. If I did not have your PA4 this morning when I went to download, I sent you an email through Canvas. So if you didn't get an email from me, you should be good. Or your Canvas email is broken, one or the other. If you were not able to upload, come and see me today. I have short office hours at 12. I'm also around at 2 o'clock after 2:15 class. So come and find me if you're having troubles with the upload. And we'll get that squared away. So any remaining questions on PA4, binary search trees, deletion, stuff like that?
What are trees?
What are trees? Yeah, exactly. All right, well, let's go on to PA5. So I've already made one revision to PA5 from a typo I found earlier. So this is the latest version, but if you already downloaded it, download it again. So PA5, we're doing this egg drop problem, okay, which we're going to work through in detail right now. But your goal is to basically write a program which can answer this egg drop analysis problem. So the basic setup is, you have a building with a number of floors, you have a collection of eggs, and for a given number of floors and a given number of eggs, what is the best guaranteed number of trials that you can use to determine what the tallest floor is you can drop an egg from without it cracking? Okay, so the question here, uppercase, the question is given number of identical eggs, building with a number of floors. What's the highest floor from which you can drop an egg and it'll survive? Okay, that's the question in here. What your program is doing, it's not answering that question, okay, because it depends on the specifics. What your program is doing is analyzing this situation and saying, you can answer this question with no more than 7 experiments, or 5 experiments, or 12 experiments. It's determining what's the best guaranteed number of sufficient trials. Okay? If it says, you can do this with 7 experiments, it means no matter what the situation, no matter what the floors look like or the eggs look like, 7 experiments will be sufficient to answer the question in all cases. You may be able to answer it with only 1 or 2 experiments. Okay? And you could certainly run, 1,000 experiments and answer the question, but it's saying the best you can guarantee is sufficient is 7. And there could be some setup of factors in which 6 will not be sufficient. Okay, so you're coming up with the best possible guaranteed sufficient number of trials. And so I've put sample code on the Linux server. And here's what your program should do. Ask the user for the number of floors. So how many floors should we try? It's got to be 500 or fewer. 499 floors. Okay, and how many eggs do we have at our disposal? 3,000. It's got to be 500 or fewer. We'll go with 499. Okay, and it'll tell me I can do this with 9 trials or 4 fewer. If we have 499 and we only have 2 eggs, it might take us 32 experiments to find the answer. If we have 499 floors and only 1 egg, it might take us 499 experiments. Yeah, but the number of experiments drops quickly. If you have 3 eggs, you only need 15. If you have 4 eggs, you only need 11. So the goal of your program is to come up with this number. And your program should just basically do, Ask how many floors, ask how many eggs, print out the answer, that's it. Okay, and the main program is pretty unimportant in this. I'm not assessing it, I'm not going to try tripping it up, I'm not going to put in weird numbers or, you know, blank lines or things like that. It's really just there to drive your egg function. Okay, the egg function is where all your grade is based on. So make your main program just this simple. All right, so yeah, there's different cases, right? If you got 50 floors and 50 eggs, we know we can just drop an egg from each floor, right? And eventually it'll break, and that's the floor that, you know, the floor right below that is the highest one you can drop an egg from where it doesn't break. If you have one egg, you've got to start from the first floor. Because if I have one egg and I start at floor 10 and my egg breaks, I don't have an answer to my question. It might be safe to drop it from 9 or 7 or 2 or 1, or maybe no floor is sufficiently low. So if you only have one egg, you got to start with floor 1. If it survives, then you try floor 2 and so on. So we'll take you up to whatever the number of floors is, experiments. If you have at least log base 2 of the number of floors worth of eggs, you can play high-low. So if you have 50 floors, you can drop from 25. If it survives, you can drop from 37. If it breaks, you can go halfway between 25 and 37, right? And you can divide your space in half each time, so it takes about log n trials. So that's why 500 floors, we can do it in 9 trials if we have at least 9 eggs. But if you don't have 9 eggs, if you only have 2 eggs, we can't play high-low indefinitely. If you get very lucky, you can. But as soon as one of your eggs breaks, you're down to 1 egg, and now you just have to try every possible floor, starting from the lowest. So it's the in-between cases that make this most interesting. Okay, so you're writing a function called egg. It takes 2 arguments, the number of floors and the number of eggs. It returns the smallest guaranteed number of sufficient trials. And so we can write this function recursively as follows. A few base cases. If the number of floors is less than or equal to 0, your egg function returns 0. Okay, if there's no floors, there's no floor you can drop the egg from. If your number of floors is equal to 1, then you return an answer of 1, because you simply try dropping the egg from the first floor. If it survives, your answer is 1. If it doesn't, its answer is 0. So it's only 1 trial if you have a single floor. If you only have a single egg, it's floors trials, because you start from the first and you work your way up. Okay. The middle cases, we have to use this recursive definition. So this is built on the following concept. Just like with the knapsack problem, we could choose what our first object was that we put in the bag, right? In this case, we're iterating over the possible first floor we're going to drop an egg from. And I'm calling that F. And F could be 1, 2, 3, all the way up to and including the top floor of the building. Okay, with this expression right here reflects is if I take 1 egg out of my basket and I drop it from floor F and it cracks, okay, the following things happen. 1, I have 1 fewer egg. 2, I know the magic floor is somewhere between 0 and F minus 1. It cracked from floor F. I don't have to check floor F plus 1, F plus 2, F plus 3. I know it's going to crack from those. But there's some critical floor below floor F, so somewhere between 0 and F minus 1. And I need to determine what that critical floor is using only eggs minus 1 eggs. So if I can figure out what the answer is to that scenario, right, what the smallest guaranteed sufficient number of trials is, I can add 1 to that because I just dropped an egg from floor F, right? And this 1 plus this expression will tell me the guaranteed best sufficient number of trials, assuming that I start by dropping from floor F. Okay. The other possibility, though, is I drop from floor F and the egg does not crack. Well, I still don't know where the critical floor is, but I know it's above floor F and it's at the top floor or lower. So between floor f plus 1 and floors, there's a total of floors minus f possible places to drop an egg. So I have to find which of those floors is the critical one, and I still have eggs, number of eggs left. So that highlighted expression, egg floors minus f comma eggs, that's the guaranteed sufficient number of trials that I need, assuming that my first experiment did not crack the egg. Okay, so the first experiment I dropped from floor F. I need no worse than one of those following two expressions. Okay, whatever each of those returns as its value of the egg function, right? One of those will be the number of trials that I need after this first one, depending on whether the egg cracked or not. Now, I don't know if the egg is going to crack. So if this first expression says, oh, well, in that case, you know, you can determine your answer with 2 trials. And if this case says, oh, in that case, you're going to need 10 trials, right? I have to go with the 10 because I'm looking for a guaranteed sufficient number of trials. And if I use the 2, well, you know, if my egg broke, I would have ended up needing 10. So, so I want the maximum of these 2 possibilities. I add 1 to that. This gives me the guaranteed sufficient number of trials, assuming I first drop from floor F, whether it survives or not.
And why'd you add them in?
And so what I need to do is I need to calculate this expression, assuming I first drop from floor 1, and then floor 2, and then floor 3, and so on and so forth. And I want the smallest answer from all of those possibilities. So I'm taking the minimum as F ranges from 1 to the top floor. Because it may be that if I start off with floor 1, this says you're going to need 10 trials, and if I start with floor 7, it says, oh, you're only going to need 5 trials, right? If that's the smallest number, then I'm going to say, okay, so I'm going to start with floor 7, and it's only going to need 5 trials. So I'm taking the minimum of that expression as F ranges from 1 up through the number of floors. And that minimum, that's the value of the egg function, given this number of floors and this number of eggs. So it's a minimum over F of 1 plus the maximum of these 2 expressions. So don't spend too much sweat trying to find a fancy way to do that in C. Just do it barehanded, right? Call that first egg function, save the result in A. Call the second egg function, save the result in B. If A is bigger than B, use A, otherwise use B. Okay, take the one you decide to use, add 1 to it. For F equals 1, right, save that in something called, you know, my best answer. And then make a loop as F goes from 2 to floors. Calculate that expression. If it's smaller than my best answer, set my best answer equal to that. Right, just a running minimum, basically. Don't try to make a function that can take, you know, an arbitrary number of arguments or stuff like that, or get into linked lists or weird things like that. Just a basic for loop will work. All right, so this, you got to get it just right, okay? But once you get it right, it's like there's a recursive call, okay? But there's no fancy data structures going on here. There's no list, there's no pointers anywhere in sight, there's no mallocs anywhere. It's just some C code. Okay, the trickiest part is just sort of getting that expression right. But you know, there's sample code on the server, so you can compare your answers. Okay, so the other aspect is this will call itself a huge number of times. There's lots of repeated subcases here where if we try to solve this for large values of floors and eggs, it's going to solve the same subproblem over and over and over again. It's going to take a really long time. So we want to use this idea of dynamic programming to speed up the calculation. So I will let you use a static array, 500 by 500. This means the maximum number of floors is 500, maximum number of eggs is 500. Okay? If we wanted this to work in general, we'd have to do mallocs on the fly to make this array big. Just going to let you cap it off at 500 for each argument. So make a static array 500 by 500, and this statement will initialize every entry to 0. Okay? Number of trials will always be at least one, except, when there's no floors. And so the whole deal is, when you write your function to calculate egg of floors eggs, before you do any of this stuff, right, check the save array. Okay, so I'm thinking the first argument is floors, second is eggs. Check that save array, see if it's non-zero. If it is, you've been here before, you saved the result of the calculation in that element of the array, just return that value. If that value is 0, do your recursive loop, find the minimum, the maximum, all that kind of stuff. When you get your final answer before you return, store it in the save array. Just say bracket floors, bracket eggs, set it equal to what your answer is, and then the next time you ask for that same function, it'll find it in the save array and it'll just return it from memory without doing any recursion. So that's the speed up. All right, does that make sense? So again, this is all about just sort of getting things wired correctly. But you know everything that you need to know to do this. Okay, you can do this today if you don't have anything else going. It's really just getting it all lined up. All right, and all sorts of simplifying assumptions. We've already talked about most of these. All the eggs are identical. If you crack from one floor, you'll crack from higher floors. If you survive from one floor, you'll survive from lower floors. If your egg survives, you can use it again, and it's unchanged by the experiment you just ran. Experiments are perfectly repeatable, so if it survives from this floor, it will always survive from this floor, right? It's not going to change, and so on and so forth. So those are the various simplifying assumptions. All right, so I would like your main program to be called eggtest.c. If you want other files, if you want to put your egg function in a separate file, that's fine. If you want .h files, that's fine. But I'd like your main program to be called eggtest.c. And I'd like a make file which creates an executable called eggtest. Okay, all lowercase. And I want eggtest to just do these three things. Ask the user for the number of floors. Floors comes first. Ask for the number of eggs, that's second, and then print out the answer, and then exit. And don't clear the screen, don't print out welcome messages, don't print out debug information, don't ask if I want to try again. Just take in two numbers, print an answer, and exit. Okay? And there's a sample again. All right, so this is a potential group project. If you want to work with other people, you can work in groups of up to 3 people. If you want to work alone, that's allowed also. It's up to you. But you can have one person working on the dynamic programming part, and 2 people working on the recursion, or however it makes sense to you to break it up, where you can all work together as a group. And obviously in your group you share code and you can write together and so on and so forth. So that's totally up to you. I would like one person from each group to submit through GitLab. Okay? If I get multiple submissions, I'm going to grade whichever one I find first. So when I download, it'll probably be alphabetical. So if you only want this person to submit, make sure that nobody else submits or doesn't add me as a reporter. Okay? If you want your own repository, just don't make me a reporter, and I won't see it when I try to download. But make sure one person in the group is uploading to GitLab and putting me as a reporter. Okay. Okay, I want your GitLab repository to be named eggtest, uppercase E, uppercase T. And the due date is Monday, 8 a.m. That's a week from this coming Monday. Okay, so it's not a 2-week project. 2 weeks from today is our last day of the quarter. Okay, which doesn't give me time to grade and give you feedback and so on. So it's due a week from Monday, March 9th, 8 a.m. All right, I'd like a README file in your repository. Please call it just README uppercase with no extension, no .md, no .text, and so on. just a README file, and I would like this to contain at the top the following information. Either tell me that you're working on this by yourself, okay, and put your name in there, or tell me that you're working on it with the following people, and put your name and the names of your group members in there. And please use the full name as it appears in Canvas so that I can link these together. Okay, and then if you want to put other stuff in the README file, that's totally fine. Okay, but at the very beginning, I'd like to find your name and whether you worked alone or you worked with other people. And that's what I'm going to use to record your grades. So make sure the person you're working with does this. All right, your repository, I would like to have the following things. The source code, which is eggtest.c, any other .c files that you make, any .h files that you make, anything that's used to build your executable. Okay, those are all considered source code. A make file, so I can say make and it builds your executable, and then the README. And I'd like those to be the only things in your repository. So whatever source code files you have, single make file and then a README. Yeah?
Is that header file alright?
Yeah, that's considered source code, so that's fine. .h's, .c's, all the things that go into building the final executable. All right, you're not going to present these in class. I'm going to run these myself to grade them. Okay, so last quarter we had group presentations. 223 group presentations will probably happen for the last group project. But for this one, I'll just grade it myself because we can use the lecture time. Okay, very important. For this assignment, I'm not going to take any late submissions. Okay, it's due on a Monday. Tuesday's the SLP. I'm grading SLPs. I'm getting ready for final exams and stuff like that. It's not feasible for me to have things coming in over the next few days. So no late submissions for PA5. Okay, I'll download Monday morning around 8 a.m. and whatever I have, I'll grade. Anything else gets a 0. If you've got 3 people in your group, somebody should be able to make sure that there's a repository there on time. Okay, and again, make your repository today, right? And just push your stuff over as you're going. And, you know, you go away for the weekend and you come back and it's like, oh, I forgot to upload my Git stuff. It's like, it's already there. Don't worry about it, right? But don't start trying to upload Sunday night before it's due, even though that's what the majority of the class has been doing. Push it over early, and then it's there. You don't have to worry about it, okay? Plus, you know, you get the advantage of having your stuff on Git, so if you accidentally lose your laptop or it gets wiped out or something like that, you've got your code on an off-site repository. You just pull it down and keep going. All right, plus you can coordinate with other people in your group if you want, and so on. All right, that's it for details. Questions about that? It's not a 10-day project, okay? If you think about this and work out, you know, a few examples, and get to where, you know, you understand the algorithm, it's probably a few hours to code it up. So I would say, you know, if you kind of dread doing these programming assignments, don't let it ruin your next week, right? Try to find some time, sit down with whoever you're working with, and just crank it out, you know. Get something going, and you'll probably find you get there sooner than you expect. And then, you know, you're done with 222. You can, like, relax and think about studying for the final maybe later on, but, you know, you're done with the programming part. And, of course, ask questions. All right, good. So let's talk about some other dynamic programming. We talked about knapsack. We talked about longest common subsequence. We talked about egg drop. Here's another classic is rod cutting. So here's the setup. You have a piece of metal rod, and it's, you know, say 5 inches long. And you can sell this piece of metal for, say, $20. And you could cut it into 1-inch pieces and sell those for $4 a piece, right? Or somebody could buy this and cut it themselves and sell them off for $4 a piece. But it may be that, you know, somebody wants to buy 1-inch length rods and they don't happen to have the tooling to cut this rod themselves. And they're willing to pay a premium to get this rod pre-cut. So a 1-inch piece may be worth $5. Well, if these are your two options, how do you maximize your profit from this rod, assuming you have an infinite number of customers?
You have a sub 1 inches since they have a higher profit margin for material?
Exactly. We would want to cut this into 5 1-inch pieces, sell those for $25. If we just do a 5-inch piece, it's only going to be $20. Well, we might have a pricing table for how much each of these is worth. So maybe a 2-inch piece is worth $11, and maybe 3-inch pieces are worthless to people for some reason, so we can't sell those for anything. And maybe a 4-inch piece is, you know, $14. And so the question is, with a pricing table like this, how should we cut up our rods so that when we sell the pieces, we get the maximum value? And if it's only a few possible lengths, we can sort of go through all the combinations and try to figure it out. But it's an expensive proposition as the number of pieces gets bigger. And so we can address this using the same kind of recursive structure we used for knapsack or for egg dropping. And so we could make, you know, some sort of maximum value, a function that tells us the maximum value we can get from a particular length, and it would be the largest of the following expressions. Well, I'll work with this particular table because I think it's a little easier than dealing with a lot of variables. I might cut off a 1-inch piece, which means I would get $5. And if I cut off 1 inch from here, I'm left with a 4-inch piece of metal. And I don't know if I should sell that as a 4-inch or as 2 inches or 4 1-inches or what. But whatever the best is that I can do in selling a piece of 4-inch metal is given by max val of 4. Or I could start off with a 2-inch cut, which would get me $11 plus max val of the 3 inches that are left. Or I could get no dollars plus the max val of what I get with the 2 inches that are left. Or I could get $14 plus whatever I can get by selling the 1 inch that's left. Or I could get $20 plus whatever I can get by selling a 0-inch piece of metal. And so we need a base case here. Max val of 0 equals 0, unless you're selling invisible metal. So if we try max val of a 0-length bar, it's just going to be 0. Otherwise, we can find the max val of a bar of length len by recursively calculating the values of these other lengths. And each of those calls to max val will make a series of recursive calls to others, and so on and so forth. And we may, you know, decide not to do this one, because since a 3-inch piece has no value, there's no reason we would ever want to cut 3 inches off and sell it. But so it's got the repeated substructure that we've seen before, and so on. And if you set this up as a tree, assuming that we want to calculate, all of these possibilities, you get a structure that looks something like this. All right, those are the possibilities for the first cut, and for each of those, we have to calculate max val for those lengths. And for each of those, we have to calculate max val for these lengths. And let's go down one more. And when we get down to calculating max val of 0, we don't have to recurse anymore. But each of these steps from a node to a child is a recursive call. We have to calculate max val of 3, 2, 1, and 0 in order to calculate max val of 4. And so we got all of this work. Well, dynamic programming, right, the idea of saving the values of these calls so that once we've called a value, called a function for one particular value, we remember it, right, means we don't have to do any of this. Because once we've called max val for 3, we've saved that value. And once we've called max val of 2, we don't have to do any of those, we don't have to do any of those. And if we've called max val for 1, we don't have to do those, or those, or those. Okay, so this is called pruning. This is pruning a tree. And it's chopping off entire sections of it. Right? If we can avoid this call to max val of 3, we can avoid the call to all of the branches, all the leaves coming off of that. Right? So this whole chunk of the tree goes away. And this will become, a question of calling max val for 0, 1, 2, 3, 4, and 5, and that'll be it. So tree pruning is basically what we're doing with dynamic programming. And it's just saving the values in a cache memory, a location of storage, an array, typically, so that we can record the results of our expensive calculations and not have to recalculate. All right, so questions about that? All right, let's change gears again. So we talked about stacks a while ago. I want to go through a really simple and pretty fun application of a stack, which is designing a stack-based calculator. So this is a typical data structures programming assignment. I don't usually assign this, but it's a fun one to work with. Suppose we're trying to make a calculator that will let you do something like 2 plus 3 times 4 plus 5 plus 6 times 7. Okay, so a bit of a complex calculation. We need parentheses in here because there's an order of precedence, and normally 3 and 4 we get multiplied first before added to 2. So we're grouping things together. And so when we were talking about trees, we noted that we could describe this expression with a binary tree. And the way we do that is we have our operators, our operands like 2 and 3, written as children of an operator like plus. And so this tree represents this expression. Take a 2 and a 3 and add them. And the 4 plus 5 we can write similarly with a 4 and a 5, whose parent is a plus. And this tree represents this calculation. Well, this piece of our expression says I want to take the result of this calculation and that calculation and multiply them. Well, if this is the first calculation and this is the second calculation and I want to multiply them, I can simply take those and make them children of a root which represents multiplication. So this tree corresponds to this expression. This thing, that thing, multiplied together. And now I want to take the result of that and add a 6. So I'll take that and a 6 and make them children of a plus operator. And that's all of this. And now I want to multiply that by 7. Put a 7 there. Make them children of a multiply. So there's a tree corresponding to that expression. And one of the nice things about making a tree like this is if I do a post-order traversal left-right node, I get a version of my original expression in what we call reverse Polish notation. So if I do a left-right node, well, I'm going to start here, I'm going to traverse the left subtree, which means traverse this, which means traverse this tree, left-right node. So that'll be 2, 3, and plus. And if I'm traversing this tree, right, first I traversed the left subtree, that was 2, 3 plus. Now I'm going to traverse the right subtree, which will be 4, 5 plus. And then I'm going to visit the root node, which is the asterisk. Okay, this is the traversal of this subtree. So if I was traversing this original tree with a plus at the top, first traverse the left subtree, that gives me this string. Now traverse the right subtree, gives me a 6, and then the root node is a plus. So that's just traversal of the original left subtree. My goal was to traverse this entire tree. Well, first I traversed the left subtree and I got this string. Now I'm going to traverse the right subtree, which is a 7, and then I'm going to visit the root node, which is a star. So there's the left-right node, or post order traversal, and this is what we call reverse Polish notation, or RPN. So this was the way that I mentioned old Hewlett-Packard calculators used to work. And you would type a 2 and hit an enter button, you type a 3, hit an enter button, and then you hit a plus sign, and your display would say 5. Then you hit 4, enter, 5, enter, plus, and your display would say 9. But then if you hit a star, it would take the previous thing that displayed, the 5, and the 9 you're seeing now, and multiply them, and it would say 45. Then if you said 6 plus, it would give you 45 plus 6 is 51. And then if you said 7 times, it would give you 357. And that's your final answer. Well, it turns out writing a program that can evaluate the string using reverse Polish notation is really simple if you have a stack. It's a 2-line algorithm to do this evaluation. So here's our expression we want to evaluate. So here's our algorithm. So explore the input string from left to right. All right, all my numbers are a single digit. If they were more than 1 digit, you have to do something to deal with that. Okay, so I need to know that, this was a 2 and a 3 as opposed to a 23. Don't worry about the details there. Okay, I'm just using single digits to avoid dealing with that. But, I would have spaces in between these or commas or something. Okay, so you're going to explore the input string from left to right, and we're going to do one of 2 things. So if you find an operand, push it onto the stack. If you find an operator, pop the top 2 things from the stack apply your operation, and push the result. And just keep looping until you reach the end of your string, and at the end, the final answer should be the only thing on the stack. So start going through your string. If you've got an operand, push it on the stack. If you get to an operator, pop, pop, operate, push the result. Just keep doing this. And when you're done, you got your answer. It's the thing sitting on the stack. So let's try this. So here's our stack. Top of the stack will be towards the bottom of the page. So I'll start pushing things up here and writing them down. All right, so first thing we find is the operand 2. That goes on the stack. Then we find a 3. That goes on the stack. Then we find an operator. So pop the 3, pop the 2, add them together. That's a 5. Push the 5 on the stack. Okay, now we find another operand that's a 4. Find another operand that's a 5. Now we find another plus sign. So pop, pop, 5 and 4, add them together is 9. Push that on the stack. Now we find a multiply operator. What do you do when you get an operator? Pop the top two things from the stack, 9 and 5, multiply them together is 45. Push a 45 on the stack. There's a 6, push that on the stack. There's a plus sign, pop the 45 and the 6, add them together, that's a 51. Push a 51 on the stack. There's an operand 7, push that on the stack, multiply, get an asterisk, pop off the 51 and the 7, multiply those together. That gives you a 357, push it on the stack, and now you get to the end of your input string, your null terminator or new line or whatever you're using, and the stack should have one thing on it, and that's the value of the arithmetic expression. So this is a really easy way to do arithmetic in a compiler or an interpreter or whatever system you're working on. If you have your thing in reverse Polish notation, postfix order. And you can get it in postfix by building a tree out of the original expression and then just traversing it left, right node. And that gives you a post order. And then you can use a stack. And if you're writing an interpreter, like a calculator program that you're hitting buttons and you're trying to do this evaluation, you're doing exactly what we just did here. If you're writing a compiler, it's a little different because you're trying to write code that will do this calculation when your program is running. And this may be things like, x, y plus z times, because you wanted to do something like c equals parentheses x plus y times z. Well, you turn it into postfix and you get something like xy plus z times, and then maybe c and some sort of store operation, which says pop off the c, pop off the result, and store the result in c, whatever that means, right? But in a compiler, you're writing code which will do this when your program is running. When you're compiling your program, you don't know the values of x and y and z, right? So you want to write code that will do this. Well, what would that look like? Well, you would have a stack at runtime, and you would say something like, push the value of x and push the value of y, and push pop plus pop. Right? And you would generate assembly language code, machine language code, something, whatever you're compiling to, that makes these calls. and, you know, somehow pushes the value of X. Or if you're storing your variables in a hash table, you know, call your get value function to retrieve from your hash table the value associated with the symbol X, and then take that and push it on your stack. Right? But it's fun to think about this at compile time versus runtime. Because we always write code and you know, we're doing the work when we're writing it. But think about writing code that's actually going to do some of these things while it's running, instead of just being written like while you're typing it into the editor. That's basically what a compiler does. So it's a little bit like meta programming. All right, so bring questions on PA5 Monday, but Monday we will start talking about another type of tree called a trie. So these are these really wide, very efficient trees that I mentioned a few days ago. We'll talk about tries for a day. We'll do some worksheets in class to practice using them. And then most of next week we'll spend talking about sorting and searching. And that'll probably be the bulk of the week, just going through sorting and searching algorithms.
You don't care if we enter invalid integers for the number of floors
Nope.
of the eggs?
I'm not going to try that. And I'm not going to go above 500.
So scanf will just be fine?
So scanf will be fine, yeah, in this case. All right, see you next time.